All right. We're talking about dynamics. I just want to scan through all these ideas that we've talked about over the course of the dynamics unit. So forgive me as I camera in place. We talked through the story of what's happened in this unit. So first of all, we talked about Newton's three laws, Newton's first, second, and third law. And when we talk about Newton's first law, we refer to this idea of inertia. The idea of inertia brings up the idea that objects in motion tend to stay in motion, objects at rest tend to stay at rest. And so we're speaking about about carrying on, maybe in closer to Newton's own words, carrying on in a state of motion. In a state of motion, if you're sitting still, your state of motion would be 0 meters per second. If you were in a state of motion where you were moving at 10 meters per second east, then you would continue, or you would tend to continue at that constant rate unless acted on by a net unbalanced force. At the end of the day, we are experiencing a tendency to stay in a state of motion, a tendency to stay at our velocity, whether it's stationary or whether it's moving in a direction at a non-zero velocity. And we also are acknowledging that the more mass we have, the greater inertia we have. Of course, more mass we have, the harder it is for us to change that velocity. So we're talking about a tendency. We're talking about how inertia depends on mass. And so that's the concept of inertia in Newton's first law. Newton's second law really is a law about proportionalities, saying that the force is going to be proportional to the acceleration, and the acceleration is inversely proportional to 1 over the mass, and bringing those two proportionalities together to say F equals ma, force equals mass times acceleration. And we've used that a bunch. Newton's third law, and we've heard this phrase so many times, this point, for every action force, there's an equal but opposite reaction force. And we're going to look at that with some free body diagram examples. But again, go back to your notes for more details. First, let's talk about free body diagrams. Simple case. Remember that if we were pushing on a mass, so that we were pushing perfectly horizontally, we might have a free body diagram like this, where there's a normal force, a force due to gravity, an applied force, a kinetic friction force. If we end up exceeding the static friction force and this object is sliding along. Keep in mind the difference between a free body diagram, like what I have here, as opposed to an illustration, which is the idea of a picture. And then if the person was pushing downwards on an angle, we might have a free body diagram that looks like this one. We've got an applied component in the x direction, an applied component in the y direction. The angled downward applied force, angled below the horizon, and that would be a piece of information that you might need to know, is the angle below horizon that this applied force is pointing in. And we would use that information to calculate what the normal force is going to be. Notice in this diagram, the normal force is greater than the force due to gravity, whereas in my first diagram, the normal force was the same value as the force due to gravity for the horizontal applied force. We've got a kinetic friction force, which I meant to make a little bit longer in this one than in this one. And I don't know if it's maybe marginal. Anyway, one thing that I look at and see with this one is that I've kind of overrepresented the applied force, because I've shown it in both the angled as an angled force and broken down into components. And we don't want to overrepresent any force. We don't want to double represent any force. So if I'm being formal about this and not wanting to overrepresent anything, either I would draw these pink arrows as dotted lines to make it very clear to the reader that I'm only representing the applied force once, or I would redraw the diagram with my applied force in the x direction only and my applied force in the y direction only, as opposed to including the diagonal one as well. Okay. Also, remember, we're doing reference frames for all of these guys. So maybe up would be positive and to the right would be positive. Left and down might be negative. Keep in mind as well that we're generally dealing with situations where the net force in the y direction is 0 newtons. In other words, F normal plus Fg plus F applied y are all adding up to 0 newtons. This thing is not blasting off or crashing to the center of the earth. The one exception to that might be where the applied force in the y direction exceeds or is greater than the Fg, which would mean that this thing is leaving the ground. I can't think of a situation that we've ever dealt with where we're pushing down with an applied force in the y direction that exceeds the ability of a tabletop, for example, to hold up the object. We haven't crashed through tabletops. So this is the one exception that we might throw out there, is that I think there might have been one or two questions along the way where the applied force in the y direction exceeded Fg, and this thing actually lifted off the ground, and the whole problem fell apart. If we were going to calculate the F net in the y direction, though, it would be F normal plus Fg plus F applied y. Remember that if F net y is equal to 0, we might use an expression like this to find the F normal, to take the Fg and the F applied y over to the other side. Remember that when we sub in our values, though, we have to apply the reference frame signs. So Fg and F applied y, if it was this reference frame and this diagram, would both be negative values when we sub them in. Just throwing that out there. And the Fk value would be calculated using an F normal value that would come out of this calculation. I'm going to move on to looking at an overhead problem. Let's just say that we were pulling a sled or something, and I think there were some problems like this over the course of the unit. A couple people pulling on a sled, one person pulling off in one direction, another person pulling off in another direction. We've got a north, south, east, west reference frame. Maybe we make south be positive this time, east be positive. Keep in mind, remember, north, south, east, west is not the same as up, down, left, right, like we looked at with the previous reference frame. This is an overhead as opposed to a side view. And we could break down F1 into F1x and F1y. Maybe F2 is being broken down into F2x and F2y. And that would be useful because then we could use those components. And of course, to do that, we would need to know what F1 and F2 is. We'd also need to know what the angles are relative to the reference frame. But assuming that we had that information, we could play the old SOHCAHTOA game, and we could figure out what F net x is and what F net y is by adding up F1x and F2x, adding up F1y and F2y, keeping in mind that when we sub in our values, that according to that reference frame we have over there on the left, F1y is a negative value when I sub in the values. F2y would be a positive value. F1x is positive, and F2x is also positive because they're both east. And we have to apply those reference frame positives and negatives as we calculate the magnitudes and sub the values into an expression. But then once we have those F net x and F net y values, we might use Pythagorean theorem to get the magnitude of F net. We might use tan theta to get the angle of the net force relative to the north, south, east, west reference frame. And if we were able to do that, then we could make a statement like the net force is so many newtons, and then give it a direction based on that calculated theta value of east so many degrees north, for example. Okay, I'm saying east so many degrees north because I can see that in my free body diagram over here, F1y is greater than F2y. So this would probably be some sort of an east towards the north kind of resultant force. If we did have a net force, though, and if we knew the mass, we could bring that force and that mass together, and we could figure out the acceleration, keeping in mind that the acceleration is going to have the same direction as the net force did. All right, so I want to move on to talking about Newton's third law, because that's kind of all Newton's second law free body diagram type conversation. Let's focus on Newton's third law. Remember that in Newton's third law, we talked about things like tug of wars. And so if we have person one and person two in a tug of war with one another, we could talk about force of two acting on one and force of one acting on two. Sure, there's force of two acting on one. And yeah, there's a force of one acting on two going on there. If we did a free body diagram, again, this is an illustration. This is a statement about the tensions that are going on. And this is the free body diagram. Force of two on one and force of one on two are the tension forces in this situation. And if we didn't add in static friction 2 and static friction 1, we might get the false impression that this whole system was going to implode. Look at this. These people with their red force vectors, they're going to just crash into each other. If there's not any static friction force, some traction going on there to hold them back. Then maybe we talk about something like a train. And this is a situation where we're not just sitting static, we're in motion. We've got mass 2, we've got mass 1 being pulled by the applied force of a train engine. And the free body diagrams that arise from that might look something like this. We've got normal force and gravity acting on both bodies. We've got the applied force pulling on the first cargo train or cargo car, freight car. We've got friction acting on that first car, friction acting on the second car. We've got internal tension forces, force of 1 on 2 and force of 2 on 1, linking those two train cars together, but they're two distinctly separate free body diagrams. Assumptions that might be made about a train car. Again, the train stays on the tracks unless you're otherwise told. So we haven't dealt with any train derailments. So it might be a fair assumption to say that F net Y is going to be equal to 0 newtons. And that's going to help us to recognize that F normal acting on 1 and F normal acting on 2 will be equal to their forces of gravity pulling down on them. So that was a nice simplification for train car problems, for example, or maybe it was a water skier problem where the buoyancy was treated kind of like a normal force. And then we say in the x direction, the F net for this system in the x direction would be equal to the applied force supplied by the train engine, Fk acting on car 1, Fk acting on car 2. And you could say plus force of 1 on 2 plus force of 2 on 1, because, yeah, they are in the horizontal. If I look back over here at the free body diagrams, they're a part of the F net. But since they're equal but opposite, these internal forces are always going to cancel each other out when we're talking about the net force for the whole system. And then we could say, well, what about the mass for this whole system? Well, the mass for the whole system will just be mass 1 plus mass 2, if we're just considering the freight cars here. And if we knew what the F net for the system was and the mass of the system, we could calculate the acceleration of this system, because acceleration of the system would be F net on the system divided by the mass of this system. Okay? And whatever that acceleration is, we could say, well, if I could calculate this, again, go back to the lessons to get the details on this, but if I could calculate this acceleration, it might be useful for me to just pop over here and say, isn't it true that if I know the acceleration of the system, I know the acceleration of car 1? And if I know the acceleration of car 2, if I know the acceleration of car 2, I could calculate the net force acting on car 2 if I know car 2's mass. So assuming I know mass of car 2, and I recognize that the acceleration of the system is equal to the acceleration of car 2, because this is a rigid system where all the parts of the system are accelerating together, I could calculate F net for car 2. And then I could say, well, how about I use that information and the fact that I could build an equation by looking at this free body diagram. I can say, based on this free body diagram, F net for car 2 in the x direction, because we can see that F net in the y direction is 0, they're going to cancel each other out. F net for car 2 is just the sum of those x components, Fk2 plus force of 1 acting on 2. And so I can make up a little equation based on that free body diagram. F net 2 is equal to force of 1 acting on 2 plus Fk2. And if I know Fk2, because I could calculate it using Fk equals mu k times F normal 2, and if I could calculate F net 2, because again, I know mass 2 and I know the acceleration of the whole system, so I know the acceleration of car 2, then the only unknown there would be that tension force, that force of 1 on 2. That was the kind of problem that we looked at when we looked at systems being pulled along. We looked at similar systems that were being pushed along by a pusher, maybe a couple of objects butting up against each other. And again, if you want more details on that, go back to your notes on those pushing systems. Reminder that when we're talking about kinetic friction, we're talking about that force that exists because two surfaces are sliding across each other, grinding against each other, and the harder we press those surfaces together, the harder they're going to have to be pushed to slide against each other. So it's that normal force that we're modifying as we push the two surfaces together, and that's going to increase the friction force as those two surfaces slide against each other. Keep in mind that with this train, it's not the wheels that are sliding against the ground, it's inside of the actual axle. There's going to be some rubbing inside of that axle as it spins within whatever the housing is that holds on to it. Okay, so that's where the friction force would occur, not between the wheels and the tracks, because those wheels are rolling, they're not sliding. This is not a sled. All right, let's take a look at this pulley problem. And just remember that for these pulley problems, we talked about finding the net force for a system like this. Recognize that the net force for this system might be Fg acting on 1 plus Fg acting on 2, where really it's just the forces due to gravity. They're acting like a tug of war pulling around this pulley. And if Fg2 was larger because maybe mass 2 was equal to 6 kilograms and mass 1 was equal to, 2 kilograms, we might say that, look, mass 2 is going to win this tug of war, so I'm going to make to the left be positive and to the right be negative. And then as we set up our free body diagrams, we've got our Fg2, we've got our Fg1, we've got tension forces. I could figure out what the net force on the system is by calculating Fg1 plus Fg2, recognizing that the way I've set up this reference frame, Fg1 would actually be a negative value because force due to gravity 1 is to the right, and we define right as negative. Fg2 would actually be a positive value when I sub in my values, because again, this Fg2 is to the left, and we defined left as positive. Okay, so those are little reminders to go back to. And again, if we were finding the acceleration of the system, remember that the acceleration of the system is equal to F net for the system divided by the mass of the system. Not the mass of one object, but mass 1 plus mass 2. And that's going to be something that may be important for calculating something like tension in a multi-step problem. Again, go back to the notes. These are things you want to remind yourselves of. All right. Now, since we're talking about Newton's third law, it might be worth bringing up the idea of Cavendish's experiment. Make sure that you go back and check out Cavendish's experiment, understand what's going on, what the physical setup is, and what the forces and the distances and the masses all are in that situation. But assuming that you've done that, remember, if I have two masses like these two here, maybe it's a planet and a moon, and maybe this moon is like orbiting around the planet following a curved path. Let's just say that it's following a circular path. So it's always a distance r away from the planet. And we could imagine that this is some sort of centripetal force that's keeping the moon in orbit around the planet. Cool. But really what we've got going on here is an action-reaction force where we've got force of 2 acting on 1 and force of 1 acting on 2, as these two objects are a distance r away from each other. I gotta be careful about my wording of distance away from each other. I mean their centers of mass are a distance away from each other. This r value represents the distance between the centers of mass, not the distance between their outer surfaces, okay? And when I calculate this force due to gravity, which really is an action-reaction force because they're mutually attracting each other, we would say Fg is equal to g times mass 1 times mass 2 over r squared, where g is that 6.67 times 10 to the power of negative 11 Newton meters squared per kilogram squared. And remember, since this big mass is so big, and this little mass is so little, I mean, the moon is small compared to the Earth, this little mass experiencing the same amount of force is going to experience a huge amount of acceleration as it accelerates and orbits in a circle around the Earth. This big mass will actually experience a small amount of acceleration as the moon orbits around it. And believe it or not, we didn't really talk about this in the course. If the moon experiences a large effect, orbit, the Earth actually experiences a small effect, it wobbles. And it's not so much true that the Earth or the moon orbits around the Earth. They actually both orbit around a center of mass. It's just that the center of mass, since the Earth is so much bigger than the moon, the center of mass for this system is inside of the volume of the Earth, and they both kind of wobble around that center of mass point. That's kind of a grade 12 concept, but it's worth just bringing up there just to get it out of the way. What we really used this idea, this relationship to talk about was something like recoil. And so we could talk about, now this isn't a cannonball, I wouldn't want to be too violent. This is a circus performer that's rolled themselves up into a ball that happens to look like a cannonball from this simple diagram. Sorry for my lack of detail. No violence in schools. But we do have this cannonball-shaped human that's rolled themselves up for a circus performance act. And as they blast out of the cannonball shooter, this person, Shazam, comes out of the cannon all excited. But if they have a relatively small mass, they will experience a huge acceleration. Meanwhile, this cannon, which has a relatively huge mass, actually recoils a little bit, accelerates backwards just a little bit. And so people build in little shock absorbers. We could put in springs here to represent that, or we could talk about how these kinds of cannons might actually like roll backwards. And one way to deal with that is to mount cannons on little ramps so that if the cannon does fire a human out of it and the cannon does recoil, it rolls up the ramp and then it rolls back down into position again. So a way to deal with recoil, and a way to deal with this very real situation where the action-reaction forces would be the same as the projectile gets fired out, but the masses are not the same, and so the resulting accelerations are not the same. Other situations we talked about that were sort of these action-reaction forces, maybe we could come back to Cavendish's experiment and maybe acknowledge that any two bodies, whether they're planetary or maybe smaller in scale, experience a very real attraction to each other. So these two stick people clearly experiencing attraction to one another. Now, if their masses are very small, recognize that these small masses will result in a small force of attraction, but maybe just enough to keep things interesting. Depending on the term, we may have had a chance to talk about Hooke's law. Hooke's law is this idea that ideal springs may start off at an undistorted length, and if I apply more and more force to those springs, the spring would stretch more and more. And the more force that I apply, the more stretch that I get. And so if I was going to graph that information, you'd get more and more and more stretch as you get more and more applied force. And the slope of that is going to be characteristic to a spring. We say that it's a constant for a given spring. So a given spring has an elastic constant, or Hooke's law ideal spring constant. And we could write this as a y equals mx plus b equation, except that since it goes through the origin, the b part is equal to 0. The y part we'd express as a force because that's the y-axis, the vertical axis. The horizontal axis is delta x, which is close enough to x actually, but delta x is what we use to represent the amount that the spring has been distorted by. And the slope, instead of writing m, people write it as k. K for the slope value, the constant. K is for constant. Now, because this force is restorative, in other words, if I pull on it with a force downwards, the spring tries to restore itself to its original shape. That's what it means to be elastic. It's going to try and restore itself to its original shape. So because it's a restorative force, it's working against our attempts to distort it. People tend to write this equation with a negative sign in front of the k, just to remind the reader that these ideal springs are going to have a force that returns them to their original length, which is to say that it resists a force that tries to change their shape. Okay, so that negative sign there is just to remind that it's going to work against whatever applied force is given to it. Just as a quick aside about this, though, the diagram that I showed initially was extension springs, where we're trying to stretch the spring. There is, of course, something called a compression spring, where a spring might start off long, and we think about maybe bed springs. And as you apply more and more force to it, that bed spring gets more and more compressed. So in this case, an increase in applied force causes an increase in distortion, but the increase in distortion is a compression distortion, as opposed to what we said initially, an extension distortion. And so this is where we have the idea of compression springs, but they will still generate the same graph where this delta x is how much it's been distorted by now. So the more force I apply, the more compressed the spring gets. but you'll still get a K constant out of an ideal compression spring. And that is all that I have to say about that. Talk to me if you have more questions about springs and forces and Newton's 3 laws.